Alright, so this is my second video on partial fractions, the integration technique called partial fractions, and in this video I'm going to show you a couple of harder cases than the one that we looked at in the first video. First one I want to look at is a case where we have repeated linear factors. So if I look at this fraction right here, I've got what? 2x minus 3 over x squared minus 2x plus 1. And I can split that up. I know that x squared minus 2x plus 1 is just x minus 1 squared. Now I want to split this up. Now I want to split this up into two fractions. But when I have, sorry, I'm going to erase this. I'm going to think of it, write it right here. 2x minus 3 over x minus 1 squared. When I have my factors here, I've completely factored the denominator here, but I have the same factor twice. And so the way I'm going to do this, instead of writing, you might think, oh, you do a over x minus 1 plus b over x minus 1. And it turns out that's not true. In fact, what you do when you have repeated linear factors like this is you do the first factor. First fraction is going to be what some constant a over x minus 1 over that first factor. The second one is going to be some other constant over x minus 1, your factor squared. Why it does that? That's a good question. That's a longer story, and longer than I'm going to go into right now, because I really wanted to show you how to do this. So you just need to know whenever you have repeated factors, repeated linear factors, you're going to have to do the first something over the first linear factor plus something over that linear factor squared. And if there was, if we had x minus 1 cubed over here, we'd have another one, c over x minus 1 cubed. We would go through each of the, the degrees until we got up to whatever the actual degree of the original fraction was. Okay, now we do the same thing that we did in the last video where we apply partial fractions. So think about, what you want to think about at this point is what would you do to combine these two fractions into a single fraction, pretending we don't know what a and b are now. We don't know what a and b are now. We want to say, well, we'd take this side would have to be multiplied by x minus 1 over x minus 1, right? That would give us x minus 1 squared in the denominator, and then we could combine the two numerators. This side, actually, this one we don't have to do anything to. We can just leave it as it is because it's already x minus 1 squared. So what do we end up with? We end up with a times x minus 1 plus b. That would be our new numerator once we've combined these two. And we know that has to be equal to this numerator over here, which was 2x minus 3. So ax minus a plus b equals 2x minus 3. Now we do the thing where we separate out x's, constants, and so on. So we've got ax and 2x. So that says, oh, okay, that's easy. Ax equals 2x. And we've got negative a and b and negative 3 over here. So negative a plus b equals negative 3. Okay, so I've just separated out the x terms, set them equal to each other, and all the constant terms, and set them equal to each other. Because again, I know that when I combine these, if I knew what a and b were, I would not be combining ax and the constant terms. I wouldn't be combining the x terms and the constant terms. So if ax equals 2x, well then I'll just keep this consistent, then a is going to have to be 2. It better be, at least. So that tells me that over here I've got negative 2 plus b equals negative 3, in which case b is negative 1. Okay, well that strongly suggests that I can say that the integral of 2x minus 3 over x squared minus 2x plus 1 dx is equal to a, which was over x minus 1, 2 over x minus 1, minus 1 over my second denominator, which was x minus 1 squared, dx. And again, 1 on the left here, no idea what to do with that, right? Again, I didn't go through it again, but you might try use substitution here, but you're going to end up with 2x minus 2 dx. You want 2x minus 3 dx. It's not going to work. Here, relatively straightforward. In fact, let's just do it just for the fun of it, right? If I integrate this one, I'm going to get 2 ln absolute value x minus 1. And here I'm going to get 1 over x minus 1. And there's a little, and plus c, of course. There's a little u substitution thing I'm doing here. I'd call u x minus 1, so it's 1 over u squared. The antiderivative of which is negative 1 over u. Since I'm subtracting already, it becomes plus 1 over u, or plus 1 over x minus 1. So I end up with this answer, which is relatively nice. I mean, the integration now is not that complicated. The complicated part is figuring out how to split this up. I'm going to do another one. Another different kind of hard case. In this case, I have a weird thing up here in the numerator, and I've got two factors in the denominator, one of which is linear, x minus 1, the other of which is quadratic. So this is different from the other one. The other one, the last one we had, ended up with two linear factors, a repeated linear factors. And in the one that I did in the previous video, we had two different linear factors. Now we've got a linear factor and a quadratic factor. Well, it turns out that 5x squared minus 4x plus 7 over x minus 1 times x squared plus 3 is equal to, as you might imagine, something over x minus 1 plus something over x squared plus 3. Just like in the previous video, previous examples, we got something over the one plus something over the other. In this case, just like we had before, with x minus 1, we got some constant over x minus 1. Over here, we're going to need something more than just a constant. We're going to need a linear factor, or a linear expression in the numerator. And the reason is essentially that if we have a linear factor here, then when we multiply it by this linear factor, we'll end up with the quadratic, which is ultimately what we need. The rule of thumb is that the numerator is always going to be 1 degree less than the denominator. If the denominator is a first degree expression, then the numerator is going to be a 0th degree expression. If the denominator is a 2nd degree expression, the numerator is going to be a 1st degree expression, and so on. We won't get into too many cases where we're like having to put in, we've got the denominator as a 5th degree expression, so the numerator has to be a 4th degree, because that would just be hideous, and we wouldn't bother with that. Okay, now what would I have to do? Let's think again. What do I have to do to combine these? Right? I would say, well, I'd multiply this side by x squared plus 3 over x squared plus 3. And I would multiply this fraction by x minus 1 over x minus 1. Okay? So that gives me my numerator of this whole fraction, then when I combined it, is going to be a times x squared plus 3 plus bx plus c times x minus 1. And that whole thing has to add up to whatever my original numerator was, which in this case is 5x squared minus 4x plus 7. Now here, just be careful. This is where I tend to make most mistakes. I got ax squared plus 3a plus bx squared minus bx plus cx minus c. And again, that's all equal to 5x squared minus 4x plus 7. Okay, now I got three kinds of terms here, right? I got x squared terms, I got x terms, and I got constants. So we'll separate them out again. Here's my two x squared terms. They're going to go with 5x squared. So I'm going to have ax squared plus bx squared equals 5x squared. Next, I've got I've got my x terms. So I've got negative bx and cx, and those are going to go with negative 4x. So negative bx plus cx equals negative 4x. And lastly, but not leastly, I've got 3a. I'm going to put this on the top because it's getting kind of messy down here. 3a and negative c. Those are my only two constants. They got to go with 7. So I got 3a minus c equals 7. Okay, now I got 3 variables, 3 equations, so I can solve this. See, what did I do here? I just went with a, oops, this color, a plus b equals 5, which means that b is 5 minus a. This one, well, negative bx plus cx is negative 4, so negative b plus c is negative 4. And if I know b is 5 minus negative, if b is 5 minus a, then negative 5 plus a plus c equals negative 4, in which case a plus c equals 1. And then I can bring that over here, and I'll just add them up. 4a on this side, these cancel out. 8, so a equals 2, in which case, well, b is 5 minus a, so that's 5 minus 2 is 3. And 2 plus c equals 1, so c better be negative 1. Okay. So, when I go back, remember what we started with was the integral of 5x squared minus 4x plus 7 over x minus 1, x squared plus 3 dx. And now we can say, oh, well, that's equal to 2a, was our 2, over x minus 1. That was our first factor. These brackets. 2 over x minus 1 plus bx plus c, 3x minus 1, right, bx plus c, over, what was our other factor, x squared plus 3 dx. And again, I can integrate both of these. Here it's going to be a little bit, right, that one's going to get a little nastier, but it's still going to be okay. We'll have to use, yeah, anyway, well, I think you have to use parts to do this one. I'm not going to do the integration right now, but I want to see, we've gotten to something where we can actually do this. The other one was not doable. Okay. Right, I want to do, oh yeah, one last case. Now this is, I put this up here in part because I want you to see, well, it can get more complicated, but also this is going to, I think this will clarify some things a little bit. So we've got the integral of x cubed minus 3 over x squared plus 3 squared dx. Well, we're going to split x cubed minus 3x. Now we've got repeated quadratic factors. We talked about repeated linear factors. Repeated quadratic factors work in much the same way. This is going to be something over x squared plus 3. We're going to decompose it into something over x squared plus 3 plus something over x squared plus 3 squared. Just like we did a couple cases back with this one, right? We split it up. It was x minus, the denominator was x minus 1 squared. So we split that into something over x minus 1 plus something over x minus 1 squared. Same basic strategy here. However, now we're dealing with a quadratic denominator, so our numerator will be linear. ax plus b. And it may turn out that a or b or any of these end up being 0, in which case it's not nearly as complicated as it looks. But we got to find that out doing the math. And then over here, we have a quadratic factor down here again. Now I know we're repeating it. That doesn't matter. What matters is that the factor itself is quadratic, which means that the numerator is going to be linear. Okay. Now just like in that previous one where we had repeated linear factors, all we have to do to change, to be able to combine these two fractions is multiply this one on the left by x squared plus 3 over x squared plus 3. We don't have to do anything to this one because it's already x squared plus 3 squared. If we multiply this one on the left by x squared plus 3 over x squared plus 3, then they will both of those fractions will have the same denominator. So we multiply that out, we get ax plus b times x squared plus 3 plus cx plus d. And all that's going to eventually have to add up to our original numerator, which was x cubed minus 3x. Okay, go here and multiply this out. Ax cubed plus 3ax plus bx squared plus 3b plus cx plus d equals x cubed minus 3x. All right, now we're going to end up with 4 equations and 4 unknowns. It turns out it's not going to be quite as complicated as we think. All right, so I'm not going to draw the lines again because it'll get too messy. I got x cubed term here and an x cubed term here. There's only one on each side, so I got ax cubed equals x cubed. And from that, I can say, oh, well, a better be 1. I also have, now I got my x squared terms. I got one x squared term on this side, bx squared. And over here, I have nothing, 0. So if bx squared equals 0, then will b better just be 0. Okay, pretty straightforward. Now what do I have? I've got an x term, 3ax, and another term, cx. And that corresponds to this negative 3x over here. So 3a plus c is going to have to be negative 3. Okay, well, I already know that a is 1, so I get 3 plus c equals negative 3, in which case c is negative 6. And that takes us to our last factor. We have the only thing we haven't accounted for, and sometimes it's useful to cross these out as you go through it. I didn't do that here, but it's useful. The only thing I have left on the left-hand side is d, and that's the constant term. And I have no constant on the right-hand side, so d equals 0. So d is taken care of. All right, now let's go remember what all this meant. What are all these a and b's? So I've got started out with x cubed minus 3x over x squared plus 3 squared dx. Now I know I can split this thing up into, well, ax plus b, so x, 1x plus 0, over x squared plus 3, my first factor, my first partial fraction. Okay, and then plus cx plus d, so that's negative 6x plus 0, over x squared plus 3 squared. And now I've got an integral that's a lot easier to deal with, right? This is going to be a simple case of substitution. In fact, both cases I'm going to substitute. I'm going to use u equals x squared plus 3. Yeah. Okay. So we've turned a potentially disturbing integral, upsetting, unhappy integral into a slightly happier. It's not pretty. It's not the kind of integral you want to take to prom, but it's at least something we can deal with using the techniques of integration that we already know. And again, this isn't really a technique. They call it a technique of integration. It's really an algebra technique that's going to make the integration a lot easier. Right, here's some basic guidelines that I've sort of put together as I've done a bunch of these problems, and you're just going to have to kind of do them to see how they work. But things to remember is, one is that you're in your partial fractions, the degree of the numerator should be 1 less than the possibly repeated factor in the denominator. So whatever the degree is in the numerator, you want to make it 1 less. If you've got x squared plus 1 in the denominator, you want to have ax plus b, a linear factor, in the numerator. If you've got x to the third minus 4x squared plus 7 in the denominator, then you want to have ax squared plus bx plus c. You want, if you have a third degree denominator, you want to have a second degree numerator. All right, and so on. The other thing is that when you do this factoring, when you factor the denominator, in order to split it up, in order to decompose that fraction, you want to first of all factor it completely, and then separate the different factors. If the factors are repeated, and we saw 2 cases where they were repeated, put those together, but keep the factors that are different separate. Okay? I'm going to stop this one now, and I'm going to come back and do one more problem that's going to emphasize this issue about separating the different factors.